All right. So it's time to go back to when we were talking about the nucleus, and I was saying it was the size of the tip of this pin if the atom was the size of the room, and that inside this nucleus would all be all the little neutrons and the protons. And it's not bad when there's, not too many of them, but as you move up the periodic table and there are more and more protons and more neutrons stuck inside here, it becomes unstable. It's kind of like, and that instability causes it to want to do something to become more stable. I think the best analogy is probably like, imagine your grandmother who wants to have a family reunion. But you and your family know that, like, Uncle Harold and his family can't stand Aunt Henrietta and their family, and you're trying to tactfully point this out to your grandmother, but she's not having it, but you know they can't be under the same roof, and she's saying, "Oh, it'll be fine. There's the backyard, and there's the front yard, and there's the rec room in the basement, and it'll be fine." And so the family reunion takes place, and the day of the family reunion, it's like thunder and lightning, torrential downpoured rain, so the backyard's out and the front yard's out and the basement's flooded. So everybody's in the living room, dining room area of the house, and needless to say, it's becoming unstable because I forget what I called them, Aunt Henrietta and Uncle Harold, I think, and family don't like each other, and so the energy is rising. And so the whole container, the whole house, or in this case, the whole nucleus is unstable. So your grandmother does the only thing that she knows how. She peruses the room and she picks out the things that she thinks, if I get rid of these, maybe this whole situation will be more stable. So she takes Uncle Harold and his whole family and she fires them out. And then she waits to see, does the energy of what's left calm down? And if it does, then nothing else is thrown out. But if it doesn't, then maybe Aunt Henrietta and her family's gone next. Okay, and that's what a nucleus does. So if a nucleus becomes unstable, then it will fire out a particle to try to become more stable. And if it works, then it's done. But if it doesn't work, it'll fire out another particle or group of particles. And it'll continue to do that until the energy inside the nucleus is such that the nucleus is now stable. It does this without any prompting from us, without us interfering. It's known as natural radioactivity. And this is what Pierre and Marie Curie were studying all those years ago. It was Marie originally, and then Pierre left his research and joined her. And when they were doing it, no one really knew what it was. Okay, but what happens is then it fired the unstable nucleus fires out a particle, and it might be like a proton inside, or it might be a neutron, or it might be two protons and two neutrons. Like we remember I talked about it with Rutherford's alpha particle scattering experiment. So it's called natural radioactivity or radioactive decay. And you'll often radioactive decay. You'll often hear the phrase about the decay rate, how quickly it decays. So this throwing particles out is the atom decaying, trying to go down to a more stable state. Okay? The rate at which it decays is different for each individual atom, and there is nothing you can do to speed up that rate. Okay, it is set. You can heat it. You can smash the sample up. It will not change the decay rate. Okay, natural radioactivity, radioactive decay is spontaneous, meaning it happens on its own, and there is nothing we can do to make it happen faster. Okay, and earlier I said every atom has at least one radioactive isotope, And all isotopes of all elements above said equals 83. That's bismuth. They're all radioactive, because think of how many little dudes are stuck inside the nucleus when you get 83 and above, and so they become unstable. Now, I had said there a few minutes ago, there's nothing that you can do to change the decay rate. And this decay rate has a name. It's called the half-life. And if I was a betting nun, I would say that you probably heard of this in math. The half-life is the amount of time required for half of the sample to decay, for half of the sample to disintegrate or to move into a more stable state. Okay, so half-life is a time, and it's time for half of the sample to become more stable. Now, the catch-22 is a sample will never actually ever be totally stable then, right? Because so the first half-life, half of it has become stable, and then the second half-life, half of that, and then the third half-life, half of that, and then the fourth half-life. But there'll always be some tiny fraction, right? You keep taking halves. You'll never, ever get it to be all stable. But when we're working with radioactive substances and we are worried about it being too radioactive, what we usually do is we wait until it's gone through enough half-lives that the part that's left is so tiny that it's not dangerous anymore. Okay? Now, there are several different ways to calculate the half-life. You probably saw it in exponential form in math. The way we usually use it is to avoid the exponentials, because then we can do it in our heads. MF is equal to MI over 2 to the N, where MF is the, not initial, it's the final mass or amount. So I'm saying M for mass. Sometimes it might be like the number of counts, like the number of disintegrations, but so it doesn't have to be mass, but it has to be some count of how much decay is taking place. You'll understand as we do some questions. MI is the initial, how much you've started with. Like, so maybe you've started with like 10 grams of a sample, and then your final is 2 grams. And N is the number of half-lives. So how many half-lives have passed? And N can be calculated by taking the full time that's passed and dividing it by the time for one half-life. And usually that symbol is a capital T with a little half. Okay, so this is full time, and this is time for one half-life. Time of one half-life. Okay, so we get the number of half-lives, we put it in here, and we can figure out how much sample is left. Every isotope has a specific half-life. So just like uranium doesn't have the same half-lives, same amount of time, half-life for every different isotope. Uranium-238 would be different from uranium-235. Some half-lives can be as small as 10 to the negative 23 of a second, and some can be as great as 10 to the 17th years. There is a chart in your textbook on page 621, and if you look, you will see like the isotope of hydrogen that's radioactive. Its half-life is 12.3 years. Carbon-14 that I talked about earlier, 5,730 years. Uranium, uranium-238, 4.51 times 10 to the, if only I could see, I think that's an 8 years. Okay, so the half-life ranges depending from really, really tiny, so that it would decay and become stable really quickly, to really, really long, and that's why in nuclear reactors, the leftover uranium, it's always a question of what are we going to do with it, because it's still radioactive. And lots of times when something is radioactive, we say it's hot.